All right, so in our first polar graph, we're going to take a look at the equation r equals 4 sine theta. And to do that, we're going to first take a look at our rectangular version of this, which is y equals 4 sine theta. Okay, so we're going to set up our axes for both of these. So for rectangular, we usually go from 0 to 2 pi. So let's see here. Go ahead and label these if you can count better than me and leave yourself enough space. There we go. Okay. And if we go ahead and set up the polar graph, these usually are more equally x and y axis centered because we're definitely more focused going from the inside pole out in each direction versus moving right to left or up and down. And we're going to just label these by degrees. So 0, and this is kind of like what you're used to on the unit circle, pi over 2, pi at 3 pi over 2, and we can also call 0 2 pi. All right, so let's graph this normally. So when you think back to how you graph trig functions, this number out front was called the amplitude. And if you remember what that word means, it's telling us kind of the height of each wave of our sinusoidal graphs, or the ones that kind of oscillate. So we know that sine typically starts at 0. I'm going to go ahead and make my scale here of 4 dashes. Typically, it would go up to 1, then back to 0. But in this case, we have this amplitude, or vertical stretch, of 4. So that highest peak is going to go all the way to 4, then to 0 at pi, then to -4, back to 0. And especially on the scale I have here, this isn't going to be a super noticeable transformation. It's just going to be a little bit skinnier. All right, so now we're going to come over here and try to graph the points we've just graphed here, but on a different type of coordinate grid. So what I often do is go through and write the coordinate points in terms of the radius, so to speak, or the height, and its angle. So let's go ahead and think about this. So at the origin, this one's actually pretty great for us because it's got a height of 0 and it's at the angle 0. The second point has a height of 4, which will become our radius on the polar graph, and the angle is pi over 2. Here the height is 0 and the angle is pi. Down here the height is -4 and the angle is 3 pi over 2. And then lastly, height of 0, angle of 2 pi. So as you can see, we're going to end up going through 0 3 different times. Okay, let's give this a shot. So the way that we graph these is we kind of partition 4 sections. And basically what I'm doing is I'm looking at how the graph is changing in each of these 4 chunks, right? And these 4 chunks are going to look a little bit different, but they're still going to be separated into those 4 sections on our polar graph as well. So in this first chunk, we're starting at 0 0. So I'm going to go ahead. We have a radius length of 0 at an angle of 0. So really we're not going to see much there. But this first section right here is going to be occurring between 0 and the angle pi over 2, which means it corresponds to this quadrant on our polar graph. So as my graph is changing from a radius of 0 to a radius of 4, it's also traveling through this particular quadrant, making that change. So that means I need to go ahead and maybe do some tick marks. Let's just do that before I forget, as best you can. Okay, so it's starting at a radius of 0, and through this entire section is changing to a radius of 4 by the time we get to pi over 2. So it should take that whole space, that whole time, to make that change in the radius length. Now, I'm moving to the second section now, and this represents what's happening between pi over 2 and pi. So that means it corresponds to quadrant 2, so to speak, on our polar graph. And again, our radius length is changing from a +4 at pi over 2 all the way back down to a radius of 0 by the time we get to pi. So this means that we're going to take this entire quadrant up, and we're going to changing from a radius of 4 back to a radius of 0. So something along these lines. I'm never getting perfect. It's supposed to be a circle, obviously. It never looks like a perfect circle, but the general idea is there. And now that we're back at this point, we can see what's coming next, right? From pi to 3 pi over 2, we would be working here, but we actually have a negative radius. And in polar graphs, a negative radius would mean we actually end up working in the quadrant that is diagonal, right? Because if we're going in a negative radius direction from this area, that pushes us away from it into this area. So in reality, going from 0 to negative 4 here, I'm starting at 0. If I'm going to a negative 4 radius, that means I'm really just retracing what we've already drawn. And then at 3 pi over 2, of course, I'm at negative 4 already. And then I'm going back to 0, but traveling through negative territory, right? So really I'm going back to 0 in the quadrant across from this fourth one, which means we're retracing the second half. So whenever we have functions of this form, which is basically just your plane sine and cosine with some sort of coefficient, vertical stretch, or any sort of reflection if there's a negative, they're going to end up just being circles. You'll be investigating in class the connection between the number and the positive and negative and the sine and the cosine. But just know the general design will end up giving you a circle if it's plane sine, plane cosine with just some sort of vertical stretch.